Imagine standing at the shore of an infinite ocean. You can see the waves lapping at your feet, the horizon stretching endlessly before you. But what lies beyond that line where sky meets water? Now multiply that mystery by infinity itself, and you begin to approach the profound question we're tackling today. What is the edge of the universe? Let's start with what we can actually observe, because that's where science is strongest. The observable universe has a very specific boundary, and it's not what most people imagine. It's not a wall, it's not a barrier you could crash into. It's something far more subtle and profound, a horizon in time. Right now, as you're listening to these words, you're at the center of your own observable universe. That might sound egotistical, but it's literally true. You can see roughly the same distance in every direction, about 46.5 billion light-years, creating a sphere with you at its center. Wait, you might be thinking, if the universe is only 13.8 billion years old, how can we see 46.5 billion light-years away? Shouldn't the maximum distance be 13.8 billion light-years? This is where things get deliciously weird. Space itself has been expanding while light has been traveling toward us. Imagine you're on a treadmill trying to walk toward a friend, but the treadmill keeps stretching, making the distance greater even as you walk. That's what photons experience as they cross the expanding cosmos. A galaxy whose light has taken 13 billion years to reach us is now much farther away than 13 billion light-years. The expansion of space has carried it outward during those billions of years. When we account for this expansion, the current distance to the edge of the observable universe is about 46.5 billion light-years. But here's the kicker. This edge isn't the same for everyone. An observer in the Andromeda galaxy has their own observable universe centered on them. It overlaps with ours but isn't identical. Someone in a galaxy 10 billion light-years away sees a completely different sphere of observation. Their edge includes regions of space we'll never see, and vice versa. This means there's no universal edge of the observable universe. There are as many edges as there are observers. Each conscious being in the cosmos sits at the center of their own cosmic horizon. It's simultaneously humbling and empowering. You're not at the center of the universe in any absolute sense, but you are at the center of your own observable reality. The cosmic microwave background, or CMB, gives us our clearest view of this edge. Discovered accidentally in 1964 by Arno Penzias and Robert Wilson at Bell Labs, the CMB is the oldest light in the universe. It's the afterglow of the Big Bang itself, released when the universe was only 380,000 years old. Before this moment, the universe was opaque to light. It was so hot and dense that photons couldn't travel freely. They'd immediately bump into electrons and get scattered. But as the universe expanded and cooled, electrons combined with protons to form the first atoms, mostly hydrogen. Suddenly, light could stream freely through space. That first light has been traveling ever since, for over 13.7 billion years. It's been stretched by the expansion of space from visible light into microwave radiation. Today, it arrives from every direction, creating a faint glow that permeates all of space. The CMB is our ultimate horizon in time. We cannot see beyond it because there was no light to see before it. It's like trying to look through a fog bank. The CMB marks the edge of the observable universe, not in space, but in history. It's the earliest moment we can observe directly. NASA's WMAP satellite and the European Space Agency's Planck satellite have mapped the CMB in extraordinary detail. These maps show tiny temperature fluctuations, differences of just a few hundred thousandths of a degree. These microscopic variations were the seeds that gravity amplified over billions of years to create the cosmic web of galaxies we see today. But the CMB isn't really the edge, it's more like a curtain. And we have ways to peer behind it, at least theoretically. gravitational waves offer one window. Unlike light, gravitational waves could have propagated through the early universe even when it was opaque to electromagnetic radiation. The LIGO and Virgo detectors have already detected gravitational waves from merging black holes and neutron stars. Future detectors might catch primordial gravitational waves from the first fraction of a second after the Big Bang. Neutrinos provide another glimpse beyond the CMB. These ghostly particles barely interact with matter, so they could zip through the early universe even when light couldn't. We haven't detected the cosmic neutrino background yet, but it should exist, carrying information from when the universe was only 1 second old. If these cosmic mysteries give you chills like they give me, make sure to subscribe. I'm dropping mind-blowing space content every week that you won't find anywhere else. And smash that like button, it genuinely helps more curious minds discover these videos. Takes 2 seconds, makes all the difference. Now let's venture beyond the observable universe. What lies past our cosmic horizon? The simple answer is more universe. There's no reason to think the universe suddenly ends at the edge of what we can see. That would be like thinking the ocean ends at the horizon when you're standing on a beach. The horizon is a limit of vision, not a limit of existence. Current measurements suggest the universe is either infinite or at least vastly larger than the observable portion. The Planck satellite measured the geometry of space to incredible precision and found it to be flat to within 0.4% margin of error. In a flat universe, space could extend forever in all directions. Think about that for a moment. Forever. No edge, no boundary. Just an endless expanse of space filled with galaxies, stars, and planets extending infinitely in every direction. If this is true, then somewhere out there, unimaginably far away, there might be exact duplicates of everything we see. There might even be duplicates of you. The mathematics of infinity suggests that in an infinite universe with a finite number of possible quantum states, patterns must eventually repeat. The physicist Max Tegmark has calculated that your nearest identical copy would be about 10 to the 10 to the 29 meters away. That's a 1 followed by over 10 billion zeros. A number so vast it has no physical meaning, but it's still finite. But maybe the universe isn't infinite. Maybe it's finite but unbounded, like the surface of a sphere. You could travel forever on Earth's surface without finding an edge, even though Earth's surface area is finite. The universe might be similar but in 3 dimensions instead of 2. If the universe is finite and curved, you could theoretically travel in a straight line and eventually return to where you started, like circumnavigating Earth. Light from distant galaxies might have circled the universe multiple times. We might be seeing the same galaxies at different stages of their evolution, like looking at your own back in a hall of mirrors. Astronomers have searched for evidence of this cosmic hall of mirrors effect. They've looked for matching patterns in the CMB that would indicate light has wrapped around the universe. So far, they've found nothing. If the universe is finite, it's at least hundreds of billions of light years across, far larger than what we can observe. But even discussing whether the universe is finite or infinite assumes space continues to behave normally beyond our horizon. What if it doesn't? What if there really is an edge, not of space, but of space-time itself? This brings us to one of the most profound questions in cosmology. What happened at the Big Bang? Was it truly the beginning of everything, or was it just a transition from something else? According to the standard Big Bang model, the universe began 13.8 billion years ago in a state of infinite density and temperature called a singularity. Space, time, matter, and energy all emerged from this point. There was no before because time itself began at that moment. Asking what came before the Big Bang would be like asking what's north of the North Pole. The question doesn't make sense within the framework, but many physicists are uncomfortable with singularities. They usually signal that our theories are breaking down. When general relativity predicts infinite density, it's probably telling us we need a quantum theory of gravity to understand what really happened. Several theories attempt to describe what might have preceded or caused the Big Bang. Eternal inflation, proposed by Alan Guth and others, suggests our universe is just one bubble in an eternally inflating multiverse. New universes constantly form as bubbles of space stop inflating and enter a Big Bang-like phase. In this model, there's no ultimate beginning, just an eternal process of universe creation. The cyclic universe model proposes that the universe undergoes endless cycles of expansion and contraction. The Big Bang wasn't the beginning, but rather a big bounce from a previous contracting phase. Each cycle might last trillions of years, with the universe expanding, eventually contracting, and then bouncing back in a new Big Bang. Loop quantum gravity, a candidate theory for quantum gravity, suggests space itself is quantized at the smallest scales. It's made of discrete units like pixels on a screen, but in 3 dimensions. This theory predicts that the Big Bang singularity never actually existed. Instead, there was a big bounce where the universe transitioned from a contracting phase to an expanding one. String theory offers yet another perspective. In some versions, our 3-dimensional universe is a brane floating in higher dimensional space. The Big Bang might have been caused by a collision between our brane and another one. These extra dimensions could extend infinitely or loop back on themselves, creating edges and boundaries we can't directly perceive. Speaking of scale and perspective, if you're fascinated by how impossibly vast these cosmic boundaries are, you'll be equally mind-blown by the opposite extreme. Check out my video, "You Won't Believe How Small We Are in the Milky Way," to see how even our entire solar system becomes invisible within our own galaxy. It really puts both the enormously large and incredibly small into perspective. The link is in the description below and on the card above. Now, what if we could somehow travel to the edge of the observable universe? What would we find? This is where our intuition completely fails us. You might imagine approaching a wall, a barrier, or perhaps just empty space extending forever. But the reality is far stranger. As you travel toward the edge of the observable universe, you wouldn't notice anything special about your location. The edge isn't a place in space, it's a limit in time. The galaxies near the current edge of our observable universe don't see themselves as being at any edge. They see themselves at the center of their own observable universe, just as we do. However, you would notice something peculiar about the universe around you. Looking back toward Earth, you'd see galaxies blue-shifted, their light compressed to higher frequencies as you move away from them. Looking forward, galaxies would be red-shifted, their light stretched to lower frequencies. The farther you traveled, the more extreme these effects would become. Eventually, the CMB radiation behind you would be blue-shifted into visible light, then into X-rays and gamma rays. The universe in that direction would appear to be in an earlier, hotter state. Meanwhile, the universe ahead would seem to be cooling and aging rapidly. If you could somehow travel faster than light, which physics currently says is impossible, you would eventually reach regions of space where the Big Bang hasn't happened yet from your perspective. You'd be traveling backward through cosmic history, watching the universe get younger and younger until you reach the singularity itself. But let's talk about what modern telescopes are actually showing us about the edge of the observable universe. The James Webb Space Telescope, launched on Christmas Day 2021, has revolutionized our view of the cosmic frontier. It's detecting galaxies that formed just a few 100 million years after the Big Bang, when the universe was less than 2% of its current age. These galaxies appear as tiny red smudges, their light stretched by 13 billion years of cosmic expansion. One galaxy, JD's GS Z13-0, has been confirmed to exist just 325 million years after the Big Bang. Another, Glass Z12, might be even older. These ancient galaxies are surprisingly large and mature, challenging our models of how quickly structures formed in the early universe. The Hubble Space Telescope, despite being over 30 years old, continues to push boundaries. The Hubble Ultra Deep Field and Extreme Deep Field images revealed thousands of galaxies in patches of sky that appeared empty to less powerful telescopes. Some of these galaxies are so distant their light has traveled for over 13 billion years to reach us. Ground-based telescopes are contributing too. The Atacama Large Millimeter Array in Chile detects sub-millimeter radiation from distant galaxies, piercing through cosmic dust that blocks visible light. The upcoming Extremely Large Telescope, with its 39-meter mirror, will be able to study the atmospheres of exoplanets and observe the first generation of stars. But there's a fundamental limit to how far we can see with light. As we look to greater distances, we're looking further back in time. Eventually, we reach the cosmic dark ages, the period before the first stars formed. During this era, roughly from 380,000 years to about 100 million years after the Big Bang, the universe was filled with neutral hydrogen gas that absorbed most radiation. The first stars ended the Dark Ages through a process called reionization. Their intense ultraviolet light ionized the hydrogen, making the universe transparent again. The James Webb Space Telescope is studying this crucial transition, watching the universe literally light up for the first time. Radio telescopes are probing even deeper. The 21-centimeter line emitted by neutral hydrogen offers a way to map the universe during the Dark Ages. Projects like the Square Kilometre Array, currently under construction in Australia and South Africa, will create three-dimensional maps of hydrogen distribution before the first stars formed. These observations are revealing something unexpected. The early universe was lumpier than we thought. Galaxies formed faster and grew larger than our models predicted. Supermassive black holes appeared surprisingly early, some reaching billions of solar masses when the universe was less than 1 billion years old. This is forcing cosmologists to revise their theories. Maybe dark matter behaves differently than we assumed. Maybe there was an earlier generation of massive stars we haven't accounted for. Maybe the initial conditions after the Big Bang were different from what we believed. And this brings us to a humbling realization. The more we learn about the edge of the universe, the more we discover we don't know. Every answer raises new questions. Every discovery reveals new mysteries. For instance, we've discovered that the expansion of the universe is accelerating. Something called dark energy, making up about 68% of the universe's energy content, is pushing space apart faster and faster. This means the observable universe has a future edge as well as a past one. Galaxies currently at the edge of our observable universe are being carried away by expansion faster than light can travel back to us. Their light is becoming increasingly redshifted until it fades beyond detection. In the far future, perhaps 100 billion years from now, the observable universe will contain only our local group of galaxies. Everything else will have passed beyond our cosmic horizon, lost forever. This accelerating expansion reveals something unsettling about the nature of edges in our universe. Not only is there an edge to what we can see now, but there's also an edge to what we'll ever be able to see, and that edge is shrinking, at least in terms of what new things we can discover. Right now, galaxies that are more than about 15 billion light-years away are already unreachable. Even if we could travel at the speed of light, we could never catch them. The expansion of space between us and them exceeds light speed. They're causally disconnected from us forever, existing in a part of the universe we can observe, but never visit or influence. Every second, more of the universe passes beyond this horizon of reachability. It's as if reality itself is slowly fading away, with distant galaxies winking out, not because they're dying, but because space-time is carrying them beyond any possibility of connection. The physicist Leonard Susskind calls this the causal patch. It's the region of space-time that can influence us or be influenced by us. Everything outside this patch might as well exist in another universe entirely. We can see its past, thanks to light that's already on its way to us, but its present and future are forever beyond our reach. This leads to a profound philosophical question. If we can never interact with most of the universe, never visit it, never affect it or be affected by it, does it really exist in any meaningful sense? Or is our causal patch the only real universe, with everything else being more like a cosmic movie playing on the sky? Different physicists have different opinions. Some argue that reality is reality, whether we can access it or not. Others suggest that perhaps the causal patch is all that physically exists, with the regions beyond being more like mathematical possibilities than physical places. Now let's dive into something even stranger. What if the edge of the universe isn't in space at all, but in other dimensions? String theory, one of our best attempts at a theory of quantum gravity, suggests that reality has more than the 3 spatial dimensions we experience. The most common versions require 11 dimensions total, 10 of space and 1 of time. We don't see the extra 7 spatial dimensions because they're compactified, curled up so small that we can't detect them directly. Imagine you're looking at a garden hose from far away. It appears one-dimensional, just a line. But up close you see it has a circular cross-section. It's actually a 2-dimensional surface wrapped into a cylinder. Similarly, what appears to us as a point in 3-dimensional space might actually have a complex 7-dimensional structure at scales trillions of times smaller than an atom. These extra dimensions could have edges and boundaries we can't perceive. The universe might end not at some distant location in space, but at the limits of these hidden dimensions. We could be like flatlanders, 2-dimensional beings, unable to conceive of up and down, missing most of reality's true structure. Some versions of string theory propose that our universe is a 3-dimensional brain embedded in higher dimensional space. Gravity can leak into the extra dimensions, which might explain why it's so much weaker than the other fundamental forces. Other brains might exist parallel to ours, perhaps just millimeters away in the extra dimensions, but completely inaccessible to us. If this is true, the edge of our universe might be the boundary of our brain. Step off the edge and you'd find yourself in the higher dimensional bulk. Of course, stepping off is impossible for us 3-dimensional beings. We're confined to our brain like shadows on a wall. The Large Hadron Collider has searched for evidence of extra dimensions by looking for missing energy that might have leaked into them. So far, nothing has been found. If extra dimensions exist, they're either very small or very cleverly hidden. But perhaps the most mind-bending possibility is that the universe has no edge because it's not fundamentally a physical thing at all. Some physicists, influenced by quantum mechanics, suggest that reality is fundamentally made of information, not matter or energy. In this view, the universe is more like a vast computation or a mathematical structure than a collection of physical objects. Space, time, matter, and energy are all emergent properties of information processing at the deepest level. If this is true, asking about the edge of the universe might be like asking about the edge of mathematics. Where does the number line end? What's beyond the set of all possible equations? These questions don't have answers because they misunderstand what mathematics is. It's not a physical thing with boundaries. It's an abstract structure defined by logical relationships. The physicist Max Tegmark has proposed the mathematical universe hypothesis, which states that our physical reality is a mathematical structure. We're self-aware patterns within this structure, experiencing it from the inside. The universe doesn't have mathematical properties, it is mathematics. In this view, the edge of the universe might be where mathematical consistency breaks down. Just as you can't have a square circle or a prime number divisible by 4, there might be regions of mathematical possibility that simply can't exist. The universe ends not at a wall but at the limits of logical self-consistency. This sounds abstract, but it makes testable predictions. If reality is mathematical, we should find that the laws of physics are as simple and elegant as possible while still allowing for our existence. And indeed, physicists have long been struck by the unreasonable effectiveness of mathematics in describing nature. Let's bring this back to something more concrete. What do we actually observe when we look for evidence of the universe's edge or shape? One of the most important observations comes from the cosmic microwave background. If the universe had an edge or a preferred direction, we'd expect to see it reflected in the CMB. But the CMB is remarkably uniform in all directions, varying by only about 1 part in 100,000. This isotropy suggests the universe has no center and no edge, at least within our observable region. However, there are some anomalies. The cold spot is a region of the CMB that's significantly cooler than expected. It spans about 5 degrees of sky, roughly 10 times the apparent width of the full moon. Some cosmologists have suggested it might be evidence of a collision with another universe, a place where our bubble of space bumped into another bubble in the multiverse. There's also the axis of evil, a terrible name for an interesting alignment in the CMB. The largest temperature fluctuations seem to align with the plane of our solar system, which shouldn't happen if the universe is truly uniform. It's probably a statistical fluke or a systematic error in our measurements, but it might hint at something profound about the universe's structure. The distribution of galaxies also tells us about the universe's shape. Large galaxy surveys like the Sloan Digital Sky Survey have mapped millions of galaxies, revealing the cosmic web, a vast network of galaxy clusters connected by filaments surrounding enormous empty voids. This structure is fractal-like at small scales but becomes smooth at scales above about 300 million light-years. This transition from lumpiness to smoothness is exactly what we'd expect if the universe is homogeneous at large scales but structured by gravity at smaller scales. But here's where things get weird again. Some observations suggest the universe might not be perfectly homogeneous even at the largest scales. There are hints of dark flows, bulk motions of galaxy clusters that shouldn't exist if the universe is uniform. Some researchers have proposed these flows are caused by massive structures beyond our observable universe, pulling on galaxies we can see. The Hercules Corona Borealis Great Wall, discovered in 2013, is a structure so large it challenges our assumptions about cosmic homogeneity. It spans 10 billion light-years, more than 1/10 the diameter of the observable universe. Structures this large shouldn't have had time to form since the Big Bang, yet there it is. These observations remind us that the universe is full of surprises. Every time we think we understand its large-scale structure, we discover something that doesn't quite fit. The edge of our knowledge keeps receding, like the cosmic horizon itself. And speaking of horizons, there's one more type of edge we need to discuss: the black hole event horizon. In a sense, every black hole is a miniature edge of the universe, a boundary beyond which our normal understanding of space and time breaks down. Black holes are perhaps the strangest edges in the universe. They're not edges in space, but boundaries in space-time itself. The event horizon of a black hole is the point of no return. Cross it, and you can never come back. not because of some physical barrier, but because space-time itself is curved so extremely that all paths lead inward. From the outside, an event horizon looks unremarkable. There's no wall, no barrier, no warning sign. If you were falling into a supermassive black hole, you wouldn't even notice when you crossed the horizon. It would seem like empty space. Only later, as tidal forces began to stretch you apart, would you realize your fate was sealed. But from the perspective of someone watching from outside, you would never quite cross the horizon. Time dilation becomes infinite at the boundary, so they would see you slow down and freeze at the edge, your image gradually red-shifting into invisibility. You would appear to be stuck at the edge of the universe, even as you experience falling through. This paradox has puzzled physicists for decades. Information seems to be both destroyed when it falls into a black hole and preserved on the horizon. Stephen Hawking spent the last years of his life working on this information paradox, eventually proposing that information is stored in a highly scrambled form on the horizon and can theoretically be recovered through Hawking radiation. Some physicists have proposed that black holes might actually be edges to other universes. The math of general relativity suggests that the singularity at a black hole's center might connect to a white hole in another region of space-time, essentially a black hole running in reverse, spewing matter and energy outward. Our entire universe might have emerged from a white hole, making the Big Bang the other side of a black hole in a parent universe. This idea, while speculative, has led to fascinating models like Lee Smolin's cosmological natural selection. Maybe universes reproduce through black holes, with each new universe having slightly different physical constants. Universes that produce many black holes have more descendants, leading to a kind of cosmic evolution that naturally produces universes friendly to black hole formation, and coincidentally, to life. The holographic principle takes the connection between horizons and edges even further. Based on insights from black hole physics, it suggests that all the information in a volume of space can be encoded on its boundary. The three-dimensional universe we experience might be a projection of information stored on a two-dimensional surface at the edge of space. This sounds bizarre, but it's supported by sophisticated mathematics. The AD-CFT correspondence discovered by Juan Maldacena in 1997 shows that certain gravitational theories in a volume are exactly equivalent to quantum theories on the boundary of that volume. It's like discovering that everything happening inside a snow globe is completely determined by patterns on the glass surface. If the holographic principle is correct, then the edge of the universe isn't just a boundary, it's where the real action is. We three-dimensional beings might be illusions, projections of the true reality existing at the cosmic boundary. The edge wouldn't be empty. It would contain all the information needed to reconstruct everything within. But let's step back from these mind-bending possibilities and talk about something more immediately observable. What about the edges of structures within the universe? Galaxies have edges, though they're not sharp boundaries. Stars become progressively rarer as you move outward from a galaxy's center, eventually trailing off into the cosmic void. But dark matter halos extend far beyond the visible stars. Our Milky Way's dark matter halo might extend over 1 million light-years from the center, encompassing smaller satellite galaxies like the Magellanic Clouds. Galaxy clusters have even fuzzier edges. They're bound by gravity, but determining exactly where one cluster ends and intergalactic space begins is somewhat arbitrary. Gas between galaxies in a cluster can be hotter and denser than gas within isolated galaxies, blurring the distinction between inside and outside. The largest structures in the universe are the cosmic filaments and walls that make up the cosmic web. These structures don't really have edges at all. They gradually fade into the surrounding voids. It's like asking where a mountain range ends. You can identify the peaks and valleys, but the exact boundary is a matter of definition. Cosmic voids, the empty regions between filaments, might be the closest things to true edges within the observable universe. Some voids are nearly 1 billion light-years across, containing almost no galaxies. But even voids aren't completely empty. They contain diffuse gas, dark matter, and the occasional dwarf galaxy. The difference between void and filament is one of degree, not kind. What's fascinating is that these structures, filaments, walls, and voids, seem to repeat at larger and larger scales until they reach the homogeneity scale around 300 million light-years. It's almost as if the universe has a characteristic pattern that emerges from the interplay of gravity and expansion. The Sloan Great Wall, discovered in 2003, is one of the largest coherent structures we've found. It's a galaxy filament roughly 1.4 billion light-years long, containing thousands of galaxies arranged like pearls on a cosmic string. Standing on a planet within the Great Wall and looking along its length, you'd see a river of galaxies stretching across the entire sky. These massive structures raise profound questions about cosmic beginnings. How did such enormous patterns emerge from the nearly uniform early universe? The answer lies in quantum fluctuations during cosmic inflation, the period of exponential expansion in the first fraction of a second after the Big Bang. During inflation, microscopic quantum fluctuations were stretched to cosmic scales. Regions that were slightly denser than average had stronger gravity, attracting more matter over time. These tiny seeds, no more than 1 part in 100,000 variations in density, grew over 13.8 billion years into the cosmic web we see today. The BICEP and Keck array experiments at the South Pole are searching for evidence of these primordial fluctuations in the polarization of the CMB. They're looking for a specific pattern called B modes that would be smoking gun evidence of gravitational waves from inflation. A detection would tell us about the universe when it was only 10 to the negative 35 seconds old, the closest we can get to the ultimate edge of time. Speaking of time edges, we need to discuss the beginning and end of the universe. These are edges not in space but in temporal existence itself. The Big Bang represents the past edge of time, at least in our universe. We can trace cosmic history back to about 10 to the negative 43 seconds after the beginning, the Planck time, before our physics breaks down. Before that moment, our concepts of space and time might not even apply. It's not that we don't know what happened before, it's that before might be meaningless. The Planck time isn't just an arbitrary cutoff. It's the scale at which our separate theories of quantum mechanics and general relativity must merge into a single theory of quantum gravity. Without such a theory, we literally cannot describe what the universe was like at earlier moments. Several candidates for quantum gravity offer different pictures of the earliest moments. Loop quantum gravity suggests that space is quantized into discrete chunks at the Planck scale, about 10 to the negative 35 meters. At this scale, there's no such thing as smooth, continuous space. Reality becomes grainy, like a photograph viewed too closely. In this framework, the Big Bang singularity is replaced by a big bounce. The universe didn't emerge from nothing but transitioned from a previous contracting phase. Time extends infinitely into the past, with cycles of expansion and contraction replacing the idea of a definite beginning. The temporal edge dissolves into an eternal cycle. String theory offers a different picture. The fundamental entities aren't point particles, but tiny vibrating strings of energy. Different vibration patterns correspond to different particles. In some string theory models, the universe has always existed in some form, with the Big Bang being a transition between different states rather than an absolute beginning. The Hartle-Hawking no-boundary proposal, developed by Stephen Hawking and James Hartle in 1983, suggests that time itself becomes space-like at the beginning. Imagine the universe as a sphere with the Big Bang at the South Pole. You can ask what's south of the South Pole, but the question has no answer. There's no boundary, just a smooth, rounded beginning where time gradually becomes more time-like as you move away from the origin. This proposal eliminates the need for an initial singularity or a moment of creation. The universe simply is, without requiring an external cause or a moment when time began. It's self-contained, with no edge in time, just a region where time behaves differently. But what about the future edge of time? Will the universe exist forever, or will it eventually end? Current observations strongly favor eternal expansion. Dark energy is pushing space apart at an accelerating rate, and there's no sign it will stop. If this continues, the universe will expand forever, growing ever colder and emptier. This future is called the Big Freeze or heat death. Galaxies will continue forming stars for perhaps another 100 trillion years, but eventually star formation will cease as gas runs out. The last red dwarf stars, which burn their fuel incredibly slowly, will finally flicker out after trillions of years. The universe will be left with stellar remnants, white dwarfs, neutron stars, and black holes, slowly cooling in an ever-expanding void. White dwarfs will take quadrillions of years to cool completely, eventually becoming black dwarfs, invisible lumps of carbon and oxygen drifting through space. We've never observed a black dwarf because the universe isn't old enough for any to have formed yet. Black holes will be the last macroscopic objects, but even they aren't eternal. Stephen Hawking showed in 1974 that black holes emit radiation due to quantum effects near their event horizons. This Hawking radiation causes black holes to slowly evaporate over unimaginably long timescales. A stellar mass black hole would take about 10 to the 67th years to evaporate. That's a 1 followed by 67 zeros, longer than any timescale we've discussed so far. But even the supermassive black holes at the centers of galaxies would eventually vanish, taking perhaps 10 to the 100th years to completely evaporate. After the black holes are gone, the universe will contain only scattered particles, electrons, positrons, photons, and neutrinos, drifting through an expanding void. The density will become so low that particles might never encounter each other again. Time will effectively lose meaning because nothing will happen. This is the ultimate edge of time, not a hard boundary, but an asymptotic approach to eternal emptiness. The universe won't end so much as fade away, like the last notes of a symphony dissolving into silence. But perhaps dark energy has surprises in store. We don't actually know what dark energy is, just that it makes up about 68% of the universe's energy and causes accelerating expansion. If dark energy behaves differently than we assume, the universe's future could be very different. One possibility is the Big Rip. If dark energy strengthens over time, the acceleration will become more extreme. Eventually, expansion will overcome the forces holding structures together. First, galaxy clusters will be torn apart, then individual galaxies, then solar systems, then planets, then atoms themselves. In the final fraction of a second, space would expand so violently that it would tear apart atomic nuclei and perhaps even the fabric of space-time itself. Current observations don't favor the Big Rip. Dark energy appears to be constant, not strengthening, but we can't rule it out. The universe might end not with a whimper, but with everything being ripped apart simultaneously. Another possibility is that dark energy might weaken or reverse. If it does, gravity could eventually halt and reverse the expansion, leading to a big crunch. The universe would contract, galaxies would merge, temperatures would rise, and eventually everything would collapse back into a singularity. This might trigger a new Big Bang, creating a cyclic universe that eternally expands and contracts. Some models suggest the universe could undergo a phase transition, like water freezing into ice. Our current vacuum state might not be the lowest energy state possible. If the universe tunnels to a lower energy state, a bubble of true vacuum would form and expand at the speed of light, converting everything it touches into a completely different kind of space with different physical laws. We would have no warning. The bubble would arrive at the speed of light, destroying us before we could see it coming. This vacuum decay scenario is unlikely, but not impossible. Measurements of the Higgs boson suggest our vacuum might be metastable, meaning it could decay given enough time. But enough time here means something like 10 to the 500th years, far longer than the age of the universe, and probably longer than anything else we've discussed. So where does all this leave us regarding the edge of the universe? We've discovered that the concept of an edge is far more complex than it initially appears. The observable universe has a horizon that limits what we can see, but it's not a physical boundary. Space might extend infinitely beyond it, or it might curve back on itself in ways we can't detect. Time might have begun at the Big Bang or might extend infinitely into the past. The future might be eternal heat death or violent destruction. What's remarkable is how much we've learned despite these profound uncertainties. We know the age of the universe to within about 1%. We've mapped its large-scale structure in exquisite detail. We understand the physics that governs its evolution from a fraction of a second after the Big Bang to the present day. This knowledge has come from centuries of patient observation and theoretical work. From Galileo's first telescopic observations to the James Webb Space Telescope's infrared images of primordial galaxies, each generation has pushed the edge of knowledge a little further. And that's perhaps the most important point. The edge of the universe is also the edge of human understanding. It's where our maps say, "Here be dragons," where our theories break down and new physics must be discovered. It's not just a place in space or time, it's the frontier of human knowledge itself. Every great scientific instrument is designed to push this frontier further. The James Webb Space Telescope sees further into cosmic history than anything before it. The LIGO gravitational wave detectors hear ripples in spacetime from events billions of light-years away. The Large Hadron Collider recreates conditions from the first trillionth of a second after the Big Bang. Future instruments will push even further. The Laser Interferometer Space Antenna, or LISA, will detect gravitational waves from supermassive black hole mergers across the observable universe. Next-generation neutrino detectors might catch particles from the cosmic neutrino background, opening a window to the universe when it was only 1 second old. Proposed gravitational wave detectors might someday detect echoes from inflation itself. Each of these instruments is a telescope pointed at the edge of the universe, trying to see what lies beyond our current understanding. But perhaps the most profound edge we need to discuss isn't physical at all. It's the edge of what can be known. Are there fundamental limits to human understanding? Are there aspects of the universe that will forever remain beyond our grasp? The answer appears to be yes. Quantum mechanics imposes fundamental limits on knowledge through the uncertainty principle. We cannot simultaneously know a particle's exact position and momentum. This isn't a limitation of our instruments, it's a feature of reality itself. The universe is fundamentally fuzzy at the smallest scales. General relativity imposes its own limits. Information cannot travel faster than light, so there are regions of the universe we can never observe or influence. The cosmic horizon isn't just a practical barrier, it's a fundamental limit on what can be known from any single location. Gödel's incompleteness theorems tell us that even mathematics has limits. Any mathematical system complex enough to include arithmetic contains statements that cannot be proven true or false within that system. If the universe is mathematical in nature, as some physicists believe, then there might be truths about reality that cannot be proven from within reality itself. These limits aren't failures of human intelligence, they're features of the universe we inhabit. A universe without uncertainty would be deterministic and predictable, perhaps incapable of producing conscious observers. A universe without horizons would be causally connected everywhere, making local physics impossible. A universe without mathematical incompleteness might be too simple to generate complexity. In a sense, the edges and limits we've discovered are what make the universe interesting. They create pockets of independence where different things can happen. They allow for surprise, discovery, and wonder. A universe without edges would be uniform, predictable, and perhaps lifeless. This brings us to a deep connection between edges and existence. We exist at edges, at the boundary between order and chaos, between the very small and the very large, between the past and the future. Earth sits at the edge of the Sun's habitable zone, where water can exist as liquid. Life exists at the edge between chemistry and biology. Consciousness exists at the edge between matter and mind. Perhaps edges aren't barriers, but birthplaces. The most interesting phenomena in the universe happen at boundaries, where different phases of matter meet, where fields interact, where space-time curves. The edge of a black hole produces Hawking radiation. The edge of the observable universe preserves information about cosmic origins. The edge between quantum and classical physics gives rise to the world we experience. Let me share something that still gives me chills every time I think about it. When we look at the most distant galaxies, we're not just seeing across space, we're looking back through time. The light from galaxy GNZ11, one of the most distant known, has been traveling for over 13.4 billion years. We're seeing it as it was just 400 million years after the Big Bang. Think about what this means. That light left GNZ11 when the universe was only 3% of its current age. It traveled through expanding space for billions of years before Earth even formed. It continued its journey as our solar system condensed from a cloud of gas and dust, as life emerged in Earth's oceans, as complex organisms evolved, as humans developed civilization and eventually built telescopes capable of detecting it. Every photon from that distant galaxy is a time capsule carrying information about conditions in the early universe directly to our instruments. We're not inferring or calculating what the early universe was like, we're literally seeing it. The edge of the observable universe is a time machine showing us baby pictures of the cosmos. And here's what really bends my mind. From the perspective of those photons, no time passed at all. Due to relativistic time dilation, a photon experiences its entire journey instantaneously. From its frame of reference, it's emitted from a star in GNZ11 and absorbed by a detector on Earth in the same moment, despite 13.4 billion years passing from our perspective. This means that in a very real sense, we're in direct contact with the edge of the observable universe. Those ancient photons connect us instantaneously, from their perspective, with the cosmic frontier. We're not separated from the edge, we're touching it every time we detect light from distant sources. The cosmic microwave background takes this even further. Those photons have been traveling since the universe was only 380,000 years old. They've crossed almost the entire observable universe to reach us. When you tune an old analog TV to a channel with no station, about 1% of the static you see is CMB radiation. You're literally watching the edge of time on your television screen. Modern cosmology has revealed that we're connected to the edges of the universe in ways our ancestors never imagined. The calcium in your bones, the iron in your blood, the oxygen you breathe, all were forged in the nuclear furnaces of dying stars billions of years ago. The atoms in your body have been part of multiple star systems, have drifted through interstellar space, have witnessed cosmic history firsthand. You are made of edge material, matter that has been processed through the most extreme conditions in the universe. Supernovae, the explosive deaths of massive stars, are edges between stability and chaos, where elements heavier than iron are created in seconds. Without these stellar edges, the chemistry of life would be impossible. Even more fundamentally, the protons in your body, the nuclei of hydrogen atoms, formed in the first microsecond after the Big Bang. They've existed for the entire history of the universe, witnessing its expansion, the formation of the first stars, the assembly of galaxies, and eventually becoming part of you. You contain pieces of the temporal edge of existence itself. This cosmic heritage connects us to another kind of edge, the boundary between life and non-life. Somewhere in Earth's history, perhaps in warm pools or deep-sea vents, chemistry became biology. Non-living molecules organize themselves into self-replicating patterns that we call life. This transition is one of the most profound edges in the known universe. We still don't fully understand how life began. Laboratory experiments have created amino acids and other organic molecules from simple chemicals, but the leap to self-replicating systems remains mysterious. It's possible that life is incredibly rare, that we exist at a unique edge where countless unlikely events coincided. Or perhaps life is common, emerging wherever conditions allow, making biological edges abundant throughout the cosmos. The search for life beyond Earth is essentially a search for other biological edges. Mars might have harbored life when it was warmer and wetter. Jupiter's moon, Europa and Saturn's moon, Enceladus, have subsurface oceans that could support life. Even Venus's acidic clouds might contain microbial life adapted to extreme conditions. The discovery of thousands of exoplanets has expanded our search for biological edges exponentially. We now know that most stars have planets, and many of these worlds orbit within their star's habitable zone where liquid water could exist. Some might have conditions radically different from Earth, but still capable of supporting life as we don't know it. The James Webb Space Telescope is already analyzing the atmospheres of some exoplanets, looking for biosignatures, chemical combinations that might indicate life. Oxygen combined with methane, for instance, would be difficult to explain without biology, as these gases react with each other and disappear quickly without replenishment. Finding life elsewhere would reveal that biological edges aren't unique to Earth. It would suggest that the universe naturally generates life wherever conditions allow, that the edge between chemistry and biology is one that nature readily crosses. This would profoundly change our understanding of our place in the cosmos. But even if life is common, intelligent life might be rare. The edge between life and consciousness is perhaps even more mysterious than the origin of life itself. How did collections of cells develop the ability to think, to be aware, to ponder their own existence? When did the first creature look up at the stars and wonder? This edge, the emergence of consciousness, might be the most important boundary in the universe. Without conscious observers, would the universe exist in any meaningful sense? This touches on deep philosophical questions about the relationship between observation and reality. Quantum mechanics suggests that observation plays a fundamental role in determining reality. The famous double-slit experiment shows that particles behave differently when observed versus unobserved. Some interpretations of quantum mechanics propose that consciousness is necessary to collapse quantum possibilities into definite outcomes. If this is true, then conscious observers aren't just passive witnesses to the universe. We're active participants in its unfolding. The edge of consciousness becomes the edge where potential becomes actual, where the quantum fuzziness resolves into the classical world we experience. This idea, while controversial, suggests a profound connection between mind and cosmos. We're not accidents in an indifferent universe, but necessary components of its self-realization. The universe becomes aware of itself through conscious beings like us. We are how the cosmos knows itself. Carl Sagan captured this beautifully when he said, "We are made of star stuff. We are a way for the universe to know itself." Every time you contemplate the edge of the universe, you are the universe contemplating its own boundaries. The observer and the observed are intimately connected. This brings us to perhaps the ultimate edge, the boundary of existence itself. Why is there something rather than nothing? Why does the universe exist at all? This question pushes beyond physics into metaphysics, beyond science into philosophy. Some physicists argue that nothing is unstable. Quantum fluctuations in empty space can spontaneously create particle-antiparticle pairs that usually annihilate immediately. But during cosmic inflation, space expanded so rapidly that some of these quantum fluctuations were stretched to cosmic scales before they could annihilate, seeding the structure of the universe. In this view, the universe is what happens when you leave nothing alone for long enough. The edge between existence and non-existence is crossed spontaneously through quantum processes. Something emerges from nothing, not through divine intervention, but through the inherent instability of nothingness itself. Others propose that the universe exists because all possible mathematical structures exist, and we happen to inhabit one that allows conscious observers. In this mathematical multiverse, every self-consistent set of equations corresponds to a real universe. The edge of existence encompasses all logical possibilities. String theory's landscape offers another perspective. The theory allows for perhaps 10 to the 500th different possible universes, each with different physical constants and laws. We exist in one that happens to allow atoms, stars, planets, and life. The edge of our universe is surrounded by a vast ocean of other possible universes, most of them sterile and lifeless. These ideas push the concept of an edge to its breaking point. If all possibilities exist, is there any edge at all? Or does existence extend through every conceivable configuration, with consciousness arising wherever conditions allow? Perhaps the most honest answer is that we don't know. The edge of the universe in all its forms marks the boundary of human understanding. We can speculate, theorize, and calculate, but ultimately we're limited beings trying to comprehend the unlimited. And maybe that's okay. Maybe the mystery is part of the beauty. A universe with no edges, no boundaries, no unknowns would be comprehensible but perhaps less wonderful. The fact that there are edges we can't cross, questions we can't answer, mysteries we can't solve, makes the journey of discovery endless. Every generation of humans has pushed against these edges, expanding the sphere of knowledge a little further. We've gone from believing Earth was the center of everything to knowing we're on a small planet orbiting an average star in one galaxy among trillions. We've discovered the expansion of the universe, dark matter, dark energy, gravitational waves, and the Higgs boson. Each discovery has revealed new edges, new boundaries to explore. The more we learn, the more we realize we don't know. The island of knowledge expands, but so does the shoreline of mystery. This isn't a failure of science. It's a feature of an inexhaustibly rich universe. Future generations will push these boundaries further. They'll have instruments we can't imagine, insights we can't foresee, and questions we haven't thought to ask. They'll look back at our current understanding the way we look back at ancient cosmologies, with respect for the effort, but amazement at how much we missed. Perhaps they'll discover that the universe has edges we haven't conceived of. Edges in dimensions we don't know exist, edges in properties we haven't discovered, edges in aspects of reality for which we don't even have words. Or perhaps they'll discover that edges are illusions, that reality is seamless and continuous in ways we can't currently perceive. Maybe the boundaries we see are artifacts of our limited perspective, like the horizon that seems to mark the edge of Earth, but actually doesn't. What we can say with confidence is that the journey of discovery will continue. Humans are edge seekers by nature. We're drawn to boundaries, to limits, to the places where knowledge ends and mystery begins. It's what drove our ancestors to cross oceans, climb mountains, and eventually reach for the stars. This drive to explore edges isn't just scientific curiosity, it's fundamental to who we are as a species. We're the only known beings who ask, what's beyond? We're the only creatures who look at a boundary and immediately want to cross it. This edge-seeking behavior might be our defining characteristic. Think about it. Every major advance in human history has involved crossing an edge. Agriculture crossed the edge from hunting-gathering to settled civilization. Writing crossed the edge from ephemeral speech to permanent record. Science crossed the edge from mythology to empirical understanding. Each boundary we've crossed has transformed us. Now we stand at the edge of edges, the cosmic boundaries that might be truly uncrossable. But even if we can't physically reach the edge of the universe, we can reach it intellectually. We can understand it mathematically. We can model it computationally. We can imagine it creatively. This intellectual reaching is uniquely human. No other species we know of contemplates abstract boundaries. A dolphin might be intelligent, but it doesn't wonder about the edge of the ocean. An octopus might solve problems, but it doesn't ponder the limits of problem-solving itself. Only humans ask questions about questions, think about thinking, explore the boundaries of exploration itself. This meta-cognitive ability, thinking about thinking, creates its own kind of edge. Where does consciousness end and mere computation begin? Is there a sharp boundary between aware and unaware, or is it a gradual transition? These questions about the edge of mind might be even more profound than questions about the edge of space. Some researchers in artificial intelligence believe we're approaching a technological edge that could transform everything. The development of artificial general intelligence that matches or exceeds human cognitive abilities. This could be the most important boundary our species ever crosses, the edge between natural and artificial consciousness. If we create minds that can improve themselves recursively, they might quickly become incomprehensible to us. They could discover edges we can't even conceive of, push boundaries we don't know exist. The edge of human understanding might not be the edge of possible understanding. This raises profound questions about the future of intelligence in the universe. Perhaps biological intelligence like ours is just a brief phase, a stepping stone to something greater. Maybe the universe's true edge explorers will be our intellectual descendants, whether artificial or enhanced biological minds. These future minds might perceive dimensions we can't access, understand physics we can't grasp, discover edges we can't imagine. They might look back at our current questions about the edge of the universe the way we look at ancient questions about the edge of the flat Earth, as quaint misunderstandings based on limited perspective. But let's return to edges we can currently comprehend. One of the most fascinating is the edge between determinism and randomness. Classical physics suggested the universe was deterministic. If you knew the position and momentum of every particle, you could predict the future perfectly. The universe was like a vast clockwork, ticking along predictable paths. Quantum mechanics shattered this view. At the smallest scales, reality is fundamentally probabilistic. You can't predict exactly when a radioactive atom will decay, only the probability. This randomness isn't due to ignorance, it's built into the fabric of reality. This creates an edge between the quantum and classical worlds. Somewhere between the scale of atoms and the scale of everyday objects, quantum fuzziness gives way to classical definiteness. But where exactly is this edge? How does quantum probability become classical certainty? This is called the measurement problem, and it remains unsolved after nearly a century of quantum mechanics. Some physicists think consciousness causes the collapse from quantum to classical. Others propose that interaction with the environment causes decoherence. Still others suggest that all quantum possibilities remain real in parallel universes. The many worlds interpretation takes this last idea to its logical extreme. Every quantum event splits the universe into multiple branches, one for each possible outcome. The edge of the universe becomes not a single boundary, but an ever-branching tree of realities with new edges created every moment. If many worlds is correct, then somewhere in the quantum multiverse there are versions of you who made different choices, lived different lives, asked different questions. The edge between actual and possible dissolves into an infinite proliferation of actualities. This connects to another profound edge, the boundary between past and future, the moment we call now. The present is the ultimate edge, the knife blade between what was and what will be. Yet physics has no explanation for why now feels special. In the equations of physics, all moments in time exist equally. Past, present, and future are human constructs, not fundamental features of reality. Some physicists embrace this view called eternalism or the block universe. In this perspective, time is like space. All moments exist simultaneously in a four-dimensional space-time block. The flow of time is an illusion created by consciousness moving through this static structure. Others argue for presentism. Only the present moment truly exists, with the past gone and the future not yet real. The universe is constantly creating itself at the edge of now, with genuine novelty emerging moment by moment. Still others propose a growing block universe where the past and present exist, but the future doesn't yet. The edge of time is constantly moving forward, adding new slices of now to the accumulated history of the universe. These aren't just philosophical musings, they have implications for the nature of the universe's edge. In eternalism, the universe has edges in time just as it might in space. In presentism, the temporal edge is dynamic, constantly moving. In the growing block view, the edge of time is the boundary between existence and not yet existence. The nature of time connects deeply to the ultimate fate of the universe. If time is eternal, then questions about the universe's beginning and end take on different meanings. The universe might be finite in time but exist eternally as a fixed structure in some higher dimensional reality. This brings us to one of the most speculative but fascinating ideas about edges, the simulation hypothesis. What if our entire universe is a simulation running on some vast computer in a higher reality? The edge of the universe would then be the limits of the simulation, the boundaries of computational resources. This might sound like science fiction, but serious physicists and philosophers have examined the idea. If it's possible to create realistic universe simulations, and if advanced civilizations tend to create many such simulations, then statistically we're more likely to be in a simulation than in the original reality. If we are in a simulation, it might have detectable edges. Perhaps at the smallest scales we'd find pixelation, a minimum unit of space and time like the Planck length and Planck time. Perhaps at the largest scales we'd find boundaries where the simulation simply ends, like the edge of a video game world. Some researchers have proposed tests for the simulation hypothesis. They've looked for evidence of computational shortcuts, like repeating patterns in the cosmic microwave background or limitations in the complexity of quantum systems. So far, no convincing evidence has been found, but the search continues. The simulation hypothesis represents the ultimate edge, the boundary between our reality and a hypothetical greater reality containing it. It's an edge we might never be able to cross or even confirm exists. Yet the possibility transforms how we think about all other edges, but whether we're in a simulation or not, the edges we've discovered remain profound. Let's talk about one more type of edge that brings together many themes we've explored: the anthropic boundary. The anthropic principle notes that the universe's physical constants seem fine-tuned for the existence of complex structures like stars, planets, and life. If the strength of gravity was slightly different, stars couldn't form. If the strong nuclear force were a bit weaker, atoms couldn't exist. The universe exists at an edge between sterility and complexity. This fine-tuning could have several explanations. Maybe there's only one possible set of physical laws and we're lucky they allow complexity. Maybe there are many universes with different constants and we naturally find ourselves in one that permits our existence. Maybe the constants were set by some process we don't understand, perhaps involving intelligence or natural selection at cosmic scales. The anthropic boundary is where physics meets philosophy. It's the edge between a universe that could support observers and one that couldn't. We exist precisely at this edge, in the narrow range of possibilities that allow matter, chemistry, biology, and consciousness. Some physicists find the anthropic principle unsatisfying, a cop-out that explains nothing. Others see it as a profound insight into why the universe is the way it is. The debate continues, but what's clear is that we exist at a special edge in the space of possible universes. This connects to the idea of the habitable zone, both for planets and for the universe itself. Earth orbits at just the right distance from the Sun for liquid water to exist, a bit closer, and we'd be like Venus with a runaway greenhouse effect, a bit farther, and we'd be like Mars, frozen and dry. We exist at the edge between fire and ice. The galaxy has its own habitable zone, too close to the center, and radiation from the dense stellar population would sterilize planets. Too far out, and there wouldn't be enough heavy elements to form rocky planets. We orbit at a comfortable distance, in the suburbs of the Milky Way. Even the cosmic epoch has a habitable zone. Too early, and the universe was too hot and chaotic for life. Too late, and all the stars will have died, leaving a cold, dark cosmos. We exist in the sweet spot when stars shine steadily and planets can support biology for billions of years. All these habitable zones are edges, boundaries between conditions that allow complexity and those that don't. The universe is full of such edges, and we naturally find ourselves at them because that's where observers can exist. This brings us to a profound realization. The edges we've been discussing aren't just abstract boundaries out there in space or time. They're intimately connected to our existence. We are creatures of edges, existing at the boundaries between order and chaos, simplicity and complexity, known and unknown. Consider your own body. You maintain a constant temperature at the edge between too hot and too cold. Your cells exist at the edge between growth and death, constantly replacing themselves. Your neurons fire at the edge between stability and change, creating the patterns we call thoughts and memories. Consciousness itself might be an edge phenomenon, emerging at the boundary between sufficient and insufficient complexity. Too few neural connections and awareness doesn't arise. Too rigid a structure and creativity disappears. We exist in the Goldilocks zone of information processing. Even our scientific understanding exists at an edge. We know enough to ask profound questions, but not enough to answer them all. We can conceive of the universe's edges, but can't reach them. We're suspended between ignorance and omniscience, and perhaps that's exactly where we need to be to remain curious. This edge position gives us a unique perspective. We're far enough from the Big Bang to study it objectively, but close enough that its light still reaches us. We're small enough to study quantum mechanics, but large enough to build instruments that reveal its mysteries. We're mortal enough to value time, but long-lived enough to accumulate knowledge across generations. In a sense, humanity itself is an edge, the boundary where the universe becomes self-aware. We're the cosmos looking back at itself, asking questions about its own nature. Every time we push against the boundaries of knowledge, we're the universe exploring its own edges. And this exploration continues. Right now, astronomers are planning the next generation of telescopes that will see even closer to the Big Bang. The extremely large telescope under construction in Chile will have a mirror 39 meters across. The proposed overwhelmingly large telescope would have been 100 meters across, though it was cancelled due to cost. Space-based telescopes are pushing boundaries too. Concepts for the Large Ultraviolet Optical Infrared Surveyor, LUVOIR, include mirrors up to 15 meters across, dwarfing even James Webb. These future observatories will see the first stars igniting, watch the first galaxies assembling, and maybe even detect signs of life on distant worlds. Gravitational wave astronomy is just beginning. LIGO and Virgo have detected dozens of black hole mergers, but they're just scratching the surface. Future detectors like the Einstein Telescope and Cosmic Explorer will be 10 times more sensitive, detecting thousands of events and probing the universe through an entirely different channel. The Square Kilometre Array, when complete, will be the world's largest radio telescope with a collecting area of 1 square kilometre spread across thousands of dishes in Australia and South Africa. It will map hydrogen throughout the universe, potentially detecting the cosmic dark ages when the first stars had yet to form. Particle physics is probing other edges. The Large Hadron Collider continues to search for new particles that might explain dark matter or reveal extra dimensions. Proposed future colliders would reach even higher energies, potentially creating conditions that existed only in the first trillionth of a second after the Big Bang. If you enjoyed this video, make sure to subscribe to the channel and give a thumbs up, and check out this other video at the left side of the screen. How big is the universe compared to the Milky Way? Discover how the Milky Way, as vast as it is just one of at least 2 trillion galaxies. See you there.